Hello, everyone. My name is Kristine Nymoen, and I'm a second-year PhD student working for Metal Earth here at Laurentian University. I'm from Norway, and I came across this project that David was working on, and I figured out, because I was working with some isotopes on my master's, I really wanted to continue that, and I saw a big opportunity here. My supervisors are Douglas Tankham. I'm just gonna, Phil Thurston, David Mole, and Jeff Marsh. And today's talk will be an update on my project, which is part of the Craton Scale project. And I'm looking at origin, petrogenesis, and architecture of the southern superior crust in both space and time. And I will focus on the Wawa subprovince. So I'd just like to take a moment to thank my project research and funding partners. And these slides just show a quick outline of my presentation. I will start with an introduction of the Craton Scale project, talk briefly about the overall goals, before I will move into the Terrain Scale project, which is also my PhD project. And here I will present some previous work and then introduce to you what I have been up to and what is to come. And then I will move on to show you some preliminary results from granitoid samples in the Wawa subprovince. It was obtained by whole rock geochemistry and oxygen isotopes in zircon. And I will wrap up the presentation with a summary. So first of all, as we know, the Superior Craton is located on the North American continent. And it is the Earth's largest Archean craton. So as we can see also from the figure here to the right, we have a variety of lithologies, which is both plutonic and granite greenstone belts, with some sedimentary basins here shown in gray. As well as the lithologies, the ages also range between 3.8 to 2.65 billion years. And I will not repeat Phil, but the overall goal for the Craton Scale project is to map out the crustal architecture of the Superior Craton to get a better understanding of the geodynamic processes that were active during the formation of this crust. And so, as we know, the Abitibi terrain is one of the world's richest terrains in terms of mineral endowment. So we're also looking into see what role these geodynamic processes played in the localization of the many ore deposits. And so that leads me to talk about the previous work that has been done, because the Superior Craton has been investigated a lot and it will continue to be investigated. And as Phil mentioned in his talk, the Metal Earth project divided the Superior Craton into 4 quadrants. And the first quadrant that was looked into was the southeastern superior part of the craton. And so that is also where my study area is. So if we zoom in this area, we can see that prior to the Craton Scale project, there existed a number of uranium lead geochronology samples. And they're shown in this picture or map, where the sedimentary rocks are indicated with gray circles, the metamorphic rocks are the purple circles, and the magmatic rocks are here, the white circles. And so David Mole, my supervisor, did some excellent work in working on compiling all these samples. And he and others have also created a database. And it's not just the uranium lead geochronology from zircons, but it's also zircon, hafnium, and oxygen isotopes in addition to trace elements. And what they did is that he used it then to image the architecture of the crust and also look into help identifying the controls on the location of the mineral systems. And so I have a figure here that was presented in Phil's talk that just shows a lutetium hafnium map that can illustrate what the work on the zircons that we are doing can result in. And so this leads me into talking about my project. So if we look at this map, we can see that the study area is the 6 provinces from eastern Wabigoon in the west through Wawa, Quetico, Pontiac, Abitibi, and Oparica. And what we did is, like, in an attempt to link together the larger Craton scale projects and the Transect projects, they formed this terrain project that is now my PhD project. And if we take a closer look at this map, it shows the newest samples that were collected in the Southeast Superior Craton by David Mole. And what we can see is that there is an obvious gap here in the Wawa subprovince. So at the beginning of this project, I started working on filling in the gaps in both time and, as we have seen from the data, also in in space, and also from the data in time. And the first work was done in the Wawa to try to collect and remove that gap. So in 2019, there was 80 samples collected from this area, and 60 of these were selected and has now been processed. And over this last summer, I was very lucky and could do field work. And so we extended the sampling out to Oparica, Abitibi, and a few samples in the Pontiac sub-province. And these are indicated with the yellow star symbols. And so another important factor for my project that adds to this Craton scale project is that I will look at incorporating the whole rock geochemistry to study the petrogenesis of these rocks. So I can look into variations of TTGs and occurrences of sanukitoids, which is important elements in the evolution. And the last thing that I will also use in this project is sulfur isotopes. And they will bring an additional data set to look at sulfur sources in the crust. And hopefully we can use this sulfur isotopes to then look if we can observe any patterns specifically for the mineral systems. And so now we'll provide you an update, because after the summer, we have now 160 new samples that have been taken from the Wawa, the Abitibi, the Oparica, Pontiac, Eastern Wabigoon, and the Quetico sub-provinces. And so that means that we have a large amount of new data, some which has been processed and some that are in the process of being processed. And what we'll get from that is approximately 160 analysis on whole rock geochemistry. We will get approximately 160 new ages from the uranium lead geochronology. We're also looking at 4,800 analysis on these 160 samples for lutetium hafnium isotopes and also trace elements. And then we'll have 1,600 new analysis on 160 samples on oxygen isotopes. And if we look at the current work, I'm now in a position where the whole rock and oxygen isotopes has been done. The uranium lead geochronology and the lutetium hafnium data are still in a stage where they're being finalized. And if we look at the new samples coming in from 2021, we have sent them out for whole rock geochemistry and mineral separation. So the next step for me would be to finalize these ages and get the lutetium hafnium data so that I can look into what samples I want to collect the sulfur isotopes from. So moving on in this presentation, I will present some of the preliminary results that we have from some granitoids in the Wawa subprovince. And as mentioned before, these are obtained from whole rock geochemistry and oxygen isotopes. So if we look first at this diagram, It shows whole rock geochemistry and how we have decided to split up the groups of samples. And first, we have been looking at the sodium-potassium ratio, which is here on the x-axis, because that ratio we can use to subdivide the granitoids into potassic and sodic populations. And so if we have a sodium-potassium ratio that is smaller than 0.7, we're looking at sodic rocks with a basaltic source. If we have a ratio that's higher than 0.7, we're looking at more potassic rocks from a more felsic source. And then in addition to that, we used strontium-yttrium ratio, shown on the y-axis, to subdivide these granitoids by source mineralogy. And so what we've done is that if we have a ratio that's less than 40, we're probably looking at a plagioclase-bearing source indicating low pressure conditions. And if we have a ratio that's larger, we're probably looking into a garnet-bearing source where you have a higher pressure. And this division between the medium pressure and the high pressure can be done based on the continent of niobium. So what we can see from here is that most of my samples are plotting on the sodic side of the diagram. Another thing that we've done is that we've looked at the whole rock, the sodium-potassium ratio, and plotted it against the delta 18 oxygen median value. And I'm not going to explain this diagram as Phil has already done that, but I just want to pay attention to the line here, which indicates when we are in the mantled zircon field. And so what the diagram tells us is that the samples from Wawa, which are indicated in the orange circles, seems to be mostly sodic, and they tend to plot towards the lighter oxygen values. And if we move away from the Wawa subprovinces, province and into Eastern Wabigoon or Abitibi, and also some samples from the Quetico, we can see that the samples become more potassic, and they show also higher oxygen values. So I've also created some contour maps so that we can look at this spatially. And in this first map, I have the sodium-potassium ratio plotted with the colors. The warmer colors are more sodic, whereas the colder colors are more potassic. So what we can see from this map is that it seems like the sodic rocks are dominating the central portion of the map, indicative of a basaltic source. And if we move out from that central part and towards the edges, the sample seems to be more potassic. And so that's more indicative of a felsic source. And if we look at the same map, but with the delta 18 oxygen isotopes, we do see similarities. It seems like the central area is dominated by the lighter oxygen values. And that's indicative of mantle-derived rocks. And if we then again study the outer parts, the color changes and the oxygen value seems to be heavier. So that's signatures of having a surface component. And another thing that I want to draw your attention to is what we see here seems to be a concentric sonation of these delta 18 oxygen values. So that's interesting. And we have integrated the oxygen isotopes and the whole rock data. And in this plot, you can see the sodium-potassium ratio, again, with the colors. But then we also have the delta 18 oxygen values here plotted as circles, where the heavier values increases in size and also have a blue color, whereas the mantle value, delta 18 oxygen, are shown with a red color and are smaller in size. So I wouldn't say there's a perfect correlation, but I do want to say that it's a broad correlation. And what most of the data indicates is that where we have these sodic sources, there seems to be mantle-like oxygen values. And the opposite is true. As we move out, we have potassic sources that have heavier oxygen values. So what I'm saying is that we probably have a more primitive mantle-derived signature in this central part. And as we move out towards the edges, we seem to have a more evolved signature with a supercrustal component. And so we also, as I said, it's not a perfect correlation, and we can look at the inconsistencies. If we look at the 3 samples up here on the edge of the cuticle margin and at the southern Wawa, we see that, oh, we have some heavy values in sodic crust. And so then you might ask why. And this could be multiple reasons for it. It could be an age control, that some of these rocks are younger. It could also be that it's an effect of the intrusions into sedimentary subprovinces. But hopefully with the data that is in process, we will have help to resolve this. We can also look at the crustal architecture and the mineral deposits. And if we look at both the sodium-potassium ratio and the delta 18 oxygen values, what we can see from the maps is that it seems that we have like most of the gold occurrences in a more sodic central part where we have the lighter oxygen values. So the initial results tell us that the central part of Wawa seemed to be dominated by sodic rocks from a basaltic source, and the oxygen values are mantle-like. So this could indicate that we have a primitive crustal component. If we move out to the exterior part, it seems like we have an area mostly dominated by potassic rocks from a crustal source, and the oxygen values becomes heavier. So this might be an evolved crustal component. And if you look at the implications for the petrogenesis, in the central part of Wawa, we don't really have an indication of a surface component. So it might be that these rocks were formed from thick mafic crust. Whereas if we look at the exterior part, we do see evidence of a surface component that is indicated by the heavier oxygen values. So maybe we're looking into a more subduction environment. 2 other points that I want to add in is also that from the broad concentric zonation that we saw from the sodium-potassium ratio and the delta 18 oxidant, they indicate that we have a nonlinear geodynamic process. So that's interesting. And when we looked at these maps with also the deposits, there might be a correlation with sodic crust and mantle oxygen values and gold systems. So to just sum this up, we see that from previous work, the isotopic mapping on the Craton Scale project has given a new level of understanding of the early geodynamic processes in the southeastern superior craton. And this PhD project aims to improve this understanding by increasing the sampling density and incorporating the whole rock geochemistry and sulfur isotopes. And what we saw is that the initial results from the Wawa subprovince shows that there is a broad spatial correlation between the sodium-potassium ratio and the zircon-oxygen isotopes. And it also indicates that we have a spatial variability of the crustal petrogenesis. So the next step for me will be to finalize this uranium-lead geochronology and the lutetium-hafnium isotopes and see what they tell me. Okay, thank you.